Hello and welcome to this H2View Showcase webinar brought to you by Parker. I'm Thomas D. Over the course of the next hour, we're going to have an in-depth exploration of hydrogen fuel cell systems and their pivotal role in the evolving landscape of sustainable transportation. We'll delve into market trends, technological drivers and system parameters shaping the adoption of hydrogen-powered buses and trucks compared to traditional internal combustion engines and electric vehicles. We'll also hear about the lessons learned using natural gas and discuss the intricacies of designing, implementing and maintaining hydrogen fuel cell systems. And you, the viewer, will also have your opportunity to get your questions answered by our panel of experts who we are now about to hear from. And with that, it's now time to hand over to your speakers today, Christian Rohr, Steve Durecki and Robert Josa of Parker.
Hello everyone. Thank you for joining us today to discuss hydrogen fuel cell systems and their pivotal role in the evolving landscape of sustainable transportation. This webinar will delve into market trends, technological drivers, and system parameters shaping the adoption of hydrogen-powered buses and trucks compared to traditional internal combustion engines and electric vehicles. We will draw from lessons learned using natural gas and discuss the intricacies of designing, implementing, and maintaining hydrogen fuel cell systems. Today, you will hear from three of our hydrogen experts, Robert Josa, Steve Durecki, and Christian Rohr. Steve is an expert in fluid conveyance products and channels across a variety of mobile and industrial markets with 34 years experience. He currently leads a team across Parker to develop the products needed to build a bridge from natural gas to hydrogen. Robert is the product manager for alternative technology in the engine mobile filtration division at Parker. He has 10 years experience in the development of filtration solutions for the transportation industry. In his most recent position, he is leading the development of filtration and separation solutions for fuel cells and hydrogen ICE applications. He monitors market trends and leads projects with OEMs and R&D teams to develop new technologies and products that fulfill customers' needs. Christian is the Market Development Manager for Fluid and Climate Controls Division Europe. He has more than 35 years experience in various fields of fluid control applications and is currently focusing on alternative fuels applications for the transportation industry. In his most recent position, he monitors market trends and leads projects with OEMs and R&D teams for fuel cells and hydrogen ICE applications. And with that, I will turn you over to Steve to discuss market trends and drivers.
Thanks, Samantha, for that introduction. And before we get started for our discussion on hydrogen fuel systems on board vehicles, we thought we'd cover some market trends and drivers first. I'd like to discuss three types of renewable energy transportation solutions available in the market today. Battery electric vehicles, which most people are familiar with, thanks to Tesla and other car manufacturers, where basically electricity is stored in the batteries, which is then used to power the electric motors. Two other solutions, which may not be as familiar, deal with storing hydrogen on board the vehicles. The first one is a fuel cell electric vehicle, where it uses that hydrogen, mixes it with oxygen from the air to generate electricity. That electricity ultimately recharges your battery as you're in motion. And the final is a hydrogen ICE, or internal combustion engine. That takes the hydrogen and burns it into an internal combustion engine to create energy. But before we get into the hydrogen fuel delivery systems, I'd like to spend 5 minutes and a couple slides talking about CNG, or compressed natural gas vehicles. We've been working with CNG vehicles for over 20 years and have gained a lot of knowledge and experience with working with CNG that will help build a bridge to hydrogen. There are a variety of vehicles today that are on the roads operating on compressed natural gas. Most commonly in the municipalities, there are CNG buses, as well as dump trucks, cement mixers, and most of the refuse companies are running CNG refuse trucks. The reason I bring up methane is because there's a lot of similarities and a lot of history that we've dealt with using compressed natural gas, basically methane at high pressures. So when we have people concerned about storing hydrogen at high pressures, I refer to the history and the longevity and the safety record we have with current vehicles on the road today. There are several applications on a CNG vehicle that will be similar in nature to hydrogen vehicles. For example, filtration is very important on a CNG vehicle as well as in a hydrogen vehicle. Fluid control, which consists of a variety of different types of valves, as well as the regulator. Both of those are also on hydrogen vehicles. And then the fluid conveyance of the gas, whether that's methane or hydrogen, involves a variety of different hoses, stainless steel tube assemblies with fittings, as well as the receptacles. Going from natural gas to hydrogen, I'd like to discuss some of the system parameters for each and where there are some differences. For example, the molecular structure for methane, also known as CNG or LNG, is CH4, which consists of 1 molecule of carbon to 4 molecules of hydrogen, whereas hydrogen is simply 2 molecules of hydrogen. The temperature required to liquefy these gases are as follows. For methane, you need to take the gas down to negative 161 degrees Celsius before it liquefies. And for hydrogen, you need to go even colder to minus 253 degrees Celsius. The onboard pressures that these gases are stored for methane is typically 250 bar or 3600 psi. And for hydrogen, because you're trying to get that same range, and hydrogen doesn't have the same power density that methane does, that's going to require some higher pressures on board. And currently there are 2 pressures that are being used in the industry, 350 bar and 700 bar. With regards to the material compatibility, for methane, there are no issues. However, when we're dealing with hydrogen, and because of the extremely small molecule size, there is such a thing as hydrogen embrittlement, and we'll be discussing that further in the presentation. And then finally, the codes and standards. Because methane has been in the industry for over 20 years, those exist today, whereas the hydrogen codes and standards are currently still, in some cases, under development. I'd like to take a few minutes to address some of the hydrogen refueling station challenges that we're coming across. First of all, how to operate a hydrogen refueling station efficiently and reliably. I think it's fair to say that there's been efficiency and reliability issues with all the early stations deployed into the public domain. The main reasons being that the available hydrogen process technology was not originally designed for a refueling environment, in combination with some very unique properties of dealing with hydrogen gas. Pressurizing, storing, and moving hydrogen under high pressures requires a range of technology that's been around for a long time. However, it hasn't been manufactured in the high volumes and the high frequency use of a 24/7, 365-day-a-year operational demand. That being said, the available technology is continuously evolving, and we are starting to see a standardization of the station design, which is a critical step towards performance and reliability, along with reduction in cost. Just as we've seen in every other technology, standardization is absolutely needed to enable the infrastructure rollout across the globe and to meet the net zero emission targets for the transportation industry. How does the hydrogen gas quality impact the operation? Dispensing hydrogen containing impurities has the potential to reduce the fuel cell efficiency and longevity of the fuel cell, something we are trying to avoid at all costs. Fortunately, there are a broad range of filtration technologies and products available on the market today. For example, Parker protects and purifies gases in some of the most critical and demanding industries involving food and beverage and life science applications. And we're leveraging those technologies and know-how to assist in the hydrogen refueling station manufacturers with their gas purification needs. When it comes to the standards for the cleanliness of the hydrogen on board your vehicle, there are two standards I'd like to reference. SAE J2719, released in 2020, and ISO 14687 from 2019. How cooling can impact the vehicle dispensing. Where most gases cool down when pushed through an orifice, such as the refueling dispenser nozzle, hydrogen actually heats up because of a thermodynamic property known as the Joule-Thomson effect. If not controlled, this could lead to overheating, which basically the composite material used inside the construction of the high pressure hydrogen fuel tanks could overheat. Those tanks are not supposed to see temperatures above 85 degrees Celsius. So to achieve this, while at the same time refueling your vehicle at the same speed that you're currently refueling your gasoline or diesel vehicle, you need to actually pre-chill the hydrogen so that it reaches the dispensing nozzle at no more than minus 40 degrees Celsius before it gets heated up when passing through the refueling nozzle and into the fueling tank. How fast is the hydrogen refueling? As mentioned earlier, the industry aim is to make both the refueling and the driving experience identical to what you're familiar with using diesel. Today, the hydrogen refueling technology already exists for passenger vehicles. For example, the Toyota Mirai takes about 3 to 5 minutes to refuel and giving you a range of over 600 kilometers. Obviously, refueling larger vehicles will take longer, but utilizing some of the high-speed refueling technologies at pressures up to 1,000 bar, which are commercially available today, we were able to reduce that time to approximately 10 to 15 minutes. Now we're going to talk about how a hydrogen fuel system works on board a vehicle. I'm going to start with covering some of the basics, and then I'm going to turn it over to my coworker. There are two types of hydrogen vehicles available in the market today. One is a hydrogen ICE, or internal combustion engine, and the other is the hydrogen fuel cell electric vehicle. Like mentioned earlier, when you burn hydrogen in an engine, it does generate nitrites, which needs to be dealt with, typically using some form of after treatment. However, a fuel cell electric vehicle is basically a chemical process that creates the electric power, with the only tailpipe emission being water. Here's an image of a hydrogen ICE fuel delivery system. As you can see in the rear, the tanks are stored at pressures of either 350 bar or 700 bar. There's a high pressure system which basically goes up until the regulator. At the regulator, which reduces it to a low pressure system. But you'll see here in the schematic, there's a variety of fluid conveyance, fluid control, and filtration products. Next, I'm going to hand it off to Robert, who's going to cover the more complex hydrogen fuel cell electric vehicle.
Okay, thank you, Steve, for the introduction into zero-emission vehicle technologies. Now we can take a look at the fuel cell system. Here you can see a simplified schematic of a fuel cell. It generates electrical power with only heat and water as byproduct. In each fuel cell system there are three major loops. We have the anode loop where the hydrogen flows. Similar to the hydrogen combustion engines, the hydrogen is stored in the tanks either in pressurized gaseous form at 350 or 700 bar or in liquefied cryogenic form. Before the hydrogen reaches the stack, it needs to be conditioned. For this, we utilize safety valves, filters, and pressure regulators. The working pressure of the stack is around 2 to 3 bar. In the fuel cell stack, during the chemical reaction, not all the hydrogen is used up, so the remaining hydrogen needs to be recirculated. In this recirculation loop, the water management and the purging sequence needs to be controlled. The second loop is the cathode loop. Here we are utilizing the environmental air. This air needs to be cleaned and compressed to around 2 to 3 bars, similar to the anode side. It needs to be cooled and humidified. On the cathode exhaust, the water that is generated in the fuel cell needs to be separated to protect the compressor. The third loop is the coolant loop. The fuel cell generates a significant amount of heat, so the thermal management is critical for the durability of the system. Additionally, the coolant liquid needs to be filtered from particles, and the conductivity needs to be controlled to protect the stack from short circuits. In this animation, you can see the function of a fuel cell. The fuel cell stack is composed of several fuel cells which are connected in series. Each fuel cell contains three primary components. We have two electrodes, the anode for the hydrogen and the cathode for the oxygen, and the proton exchange membrane in the middle as a conductive electrolyte. Each electrode is composed of the gas diffusion layer and the catalyst. The gas diffusion layer is a porous, high surface area material. The catalyst layer has typically a carbon support that is impregnated with a catalyst, usually platinum or a platinum alloy. The polymeric membrane in the middle serves as an ionic conductor. The chemical reaction on both the anode and the cathode side happens at the catalytic surface. On the anode side, as you can see, the hydrogen molecule spreads through the gas diffusion layer until it reaches the catalytic surface. Here it splits into protons and electrons. The newly formed positively charged protons permeate through the membrane to the cathode side, while the negatively charged electrons need to travel on an external load circuit to the cathode side. On this external load circuit, electricity is produced. On the cathode side, the incoming oxygen spreads through the gas diffusion layer, and at the catalytic surface, it will react with the protons that are permeating through the membrane and the electrons that are arriving on the external circuits. And they will form water molecules and residual heat. The main function on the membrane is to conduct the hydrogen protons, but to block the electrons, and it must not allow either of the gas to pass to the other side. Now we can take a look at what are the major topics that need to be considered when we are designing a hydrogen system. There are several things that need to be considered. I will take you to the filtration and humidification side of a fuel cell system, and later Christian will talk about the fluid control components, standards and certifications which are important, material compatibility, and sealing styles. The fuel cell stack is very sensitive to impurities. The quality of the hydrogen and of the air needs to be controlled before it reaches the stack. Certain gases, such as nitrogen oxide, sulfur dioxide, ammonia, toluene, and others, which are present in the air, can poison the catalytic layer. This will block the platinum catalyst and can lead to power losses because the electrochemically active surface is reduced. The poisoning effect of some of the gases can be reversible, but for others it cannot. For this purpose, it is critical that these contaminants are filtered out before the air reaches the stack. There are different types of filtration technologies that need to be combined for optimal air filtration. To protect the stack, cathode air filter is required. There are several filtration requirements which need to be considered when selecting such a product. Particle filtration is important. We need to make sure that all the particles are removed from the environmental air because this can block the gas diffusion layer and can also damage the membrane. The gas adsorption efficiency shows how well the filter can remove certain gases. The gas absorption capacity shows how much of these certain gases can be filtered out by the product. The pressure drop is also important because this will impact the performance of the compressor. There are several types of medias and filtration technologies that can be utilized for the gas absorption function. As you can see on these graphs here, there are different technologies which will have different performances depending on the gases. So we need to make sure that the correct media and the correct technology is selected in the development of such filters, and this needs to be selected based on the application requirements. The gas absorption performance is the most important of the cathode air filter. This performance can be tested according to some standardized testing methods, such as the ISO 11155-2. This basically measures the gas absorption efficiency and capacity of the filters, but the test is conducted on single gases. There are several other parameters which will impact the performance of the filter. For example, as mentioned, this ISO test is conducted on single gases. However, in the environmental air, there is always a mixture of gases. We have conducted several tests to compare the performance of single gas and gas mixtures, and this has a major impact on the performance of the filter. Similarly, the gas concentration will have an impact. The higher the concentration, the lower the efficiency of the filter. The ISO standard has a high concentration to make sure that the test can be finalized in a certain amount of period. However, in real-life conditions, this concentration is significantly lower, and this will also have a major impact on the filter. The third point would be the phase velocity on the media, basically how much of the air flows through a certain amount of area of a filter. This is critical because this needs to be tweaked correctly to make sure that you have the optimal gas performance and the optimal size of such a filter. So we looked at how different gases can poison the catalyst and impact the performance of the stack. Now we will take a look at how the humidity of the air impacts the performance of the fuel cell. The proton exchange membrane functions as a conductive electrolyte. The membrane needs to be humid to effectively transfer the protons and to block the gases from passing from one side to the other. If the membrane dries out, this will impact the proton transfer, and it will also reduce the durability and lifetime of the stack. If the membrane is not humid, this can damage the membrane itself. During the operation of the fuel cell, this will generate a large amount of water. However, this water needs to be removed from the stack to avoid flooding of the gas diffusion layer. The humidity level for the incoming air needs to be controlled. To control the humidity level, a fuel cell humidifier can be used. There are several requirements for such a product. The humidifier needs to produce the optimal level of humidity of the incoming air to the stack. Low pressure drop is desired because this will impact the performance of the compressor. The durability and reliability of the humidifier is needed. It is targeted not to have any performance drop in the humidity transfer during its lifetime. Since we are focusing on the transportation segment of trucks and buses, the size and weight of the humidifier is important. The material compatibility needs to be considered. We need to make sure that the humidifier will not leach any chemicals that can damage the stack. Currently, there are several technologies that are being utilized for humidification. The humidity transfer can be done with membrane technology. There are hollow fiber membranes and flat sheet membranes. Both of them have their advantages and disadvantages. There are also considerations of water dosing. However, it is desired not to introduce any liquid water, but rather to humidify the incoming air. Additionally to cleaning and humidifying the incoming air, there are other filtration needs in a fuel cell system. As mentioned before, the stack generates a significant amount of water on the cathode side and also on the anode side, and this needs to be separated. On the cathode side, the reason to separate the water on the exhaust, it is to protect the compressor. Balance needs to be reached between separation efficiency, pressure drop, and envelope, since these are interconnected. If a higher efficiency is required, this will bring with it a higher pressure drop or a bigger envelope. On the anode side, the water needs to be separated so that it is not recirculated with the hydrogen. Typically, the hydrogen recirculation is a passive recirculation, so the pressure drop of the unit is important. Since the product is in the hydrogen loop, material compatibility needs to be considered. Also, an automatic drain system is required. We need to make sure that only the water is drained from the filter and no hydrogen is lost during the draining procedure. Staying on the anode side, the hydrogen also needs to have a high purity, not to damage the fuel cell stack and to negatively impact the stack's performance. The cleanliness and purity is currently controlled at the hydrogen refueling stations. There are several standards which are regulating the hydrogen purity. There are, however, still concerns about this cleanliness, especially once the hydrogen production is ramped up. To protect the stack from impurities, a hydrogen filter can be utilized. Currently, the major target of the filter is to be a particle filter and to remove all types of particles that can enter the hydrogen line during refueling. However, there are also other filtration technologies such as coalescing filters that can remove all types of liquids. The filter needs to cope with the pressures of the system, whether it's assembled to the high or to the low pressure side. So the correct materials needs to be selected that are hydrogen compatible and can withstand the pressures and temperatures. Now Christian will explain the fluid management side of the fuel cell system and the different certifications and standards needed for hydrogen applications.
Thank you, Robert. I have now the pleasure to give you a brief introduction to the world of fluid management. I will focus on the most important applications, in particular the technical challenges and the demanding approvals and certification situation. We have already looked at the basic design of a complete fuel cell application, but in the next few minutes I would like to highlight a few key functions. Essentially, the system consists of the four areas, all of which have different requirements for the fluid management components. In fluid management and tank systems, the component is in direct contact with the hydrogen, while in thermal management and emissions control, coolants, air or wastewater are controlled. In our illustration, we have used different colors to represent the different media. Robert already introduced you to that scheme. And important for us is that each and every application has its own requirements and specifications to fulfill. But now let's have first a look on the typical applications. The safety shut-off valve, which are used in various points, play a very important role. But pressure control and monitoring or distribution to various consumers are also important elements in a fluid management circuit. All elements are essential for the safety and performance of the application. Some functions can be combined in systems and subsystems. As an example of such a system, particular reference can be made to the on-tank valve, in which a bleed valve, a manual safety tab, a pressure relief valve, a check valve for refueling, and sometimes additional filters are integrated, in addition to the safety shut-off valve. Another example is the fuel regulation devices, where pressure regulators are combined with safety shut-off valves, pressure relief valves, and excess flow valves. But now let's have a look to a few more functions in detail. We would like to focus today on two basic applications which we will use to describe the technical challenges, namely the safety shut-off valve and the pressure regulator. Both very important components within the fluid management system. Safety shut-off valves are often used redundantly, so we find this function in such a circuit, for example, integrated into the on-tank valve as an independent standalone component, but also integrated into the fuel regulation module. The effective assurance of functional safety is of high importance here. If we look at the challenges posed by the medium itself, the safe function for the application, but even more importantly, the safety for the user and the environment, it becomes quickly clear how important the correct definition and the design is for safe operation. For safe operation today, it is absolutely essential to automate as many functions as possible in order to avoid the human factor as a safety risk. Actual statistics from Center of Hydrogen Safety indicate that approximately 85% of hydrogen incidents are related still to the human factors. So let's take a closer look at how a safety shut-off valve in the form of a solenoid valve works. In our hydrogen application, a solenoid valve is in direct contact with the hydrogen medium. It has the task of safely and reliably controlling the medium flow and preventing leakages, both within the circuit and to the outside or into the atmosphere. To actuate it, a solenoid coil is energized by means of a supply voltage and thus brought into the desired position. For safety shut-off valves, this function is usually normally closed. The solenoid coil generates a magnetic attraction force which is used to move a solenoid armature into the desired position. For some applications, the actual medium is also used to provide additional forces with the help of the pressure differential, which can then be used to achieve higher pressure rates. When used on a vehicle, this application alone, in this case independent of the hydrogen medium, means that challenging environmental conditions must be taken into account when designing a solenoid valve. Fluctuating supply voltages must be taken into account, and safe operation is expected even within a ±30% tolerance span. This means that a valve designed for 24 volt DC can also be operated safely with 16 volts or with 32 volts. The influence of ambient temperature and media temperatures plays a major role, as do vibrations and protection against moisture, wetness and dirt. Electrical connections must also be able to withstand the stresses caused by, for example, high pressure washing. In our hydrogen application, there are also the challenges of the medium itself, which we will take a closer look at in a few minutes. Another very important part within the hydrogen cycle is the mechanical pressure regulator. This has the task of reducing the tank pressure to the fuel cell pressure required for the application. They are used to control and maintain a consistent level of hydrogen pressure within the system, which can vary dependent on the used fuel cell itself. A reliable pressure supply is essential to supply the fuel cell with the correct supply pressure and flow rate and to protect it from damages that could be caused by pressure peaks. The pressure regulator is also ideal for combining with other required functions. For example, the pressure regulator is the main component within the fuel regulation module, in which the solenoid valve, the PRV and the sensors can also be integrated. But now let's have a look to the imposed challenges and the requirements for the application. Hydrogen is the lightest element and at standard conditions is colorless, odorless, tasteless, non-toxic and highly combustible. One of the challenges for all materials is hydrogen embrittlement. Hydrogen embrittlement is a complex phenomenon involving several lengths and timescales that affects a large class of metals. It can significantly reduce the dusivity and load-bearing capacity and cause cracking and catastrophic brittle failures at stresses below the yield stress of different materials. Hydrogen can dissolve in most metals and alloys, and its interactions with crystal lattice features are a reason for concern in iron, steel, nickel, titanium, vanadium, and other metals used in engineering. Problems connected to hydrogen in materials are manifested in numerous ways. For example, stress corrosion cracking, hydrogen-induced cracking, hydrate cracking, or other deleterious effects often leading to catastrophic fracture. There are some materials suitable for hydrogen applications. Today, at least in the US and Europe, stainless steel is the preferred solution to avoid negative effects for the application. Hence, you will find in nearly every client specification a request to focus on stainless steel only. But in other regions like Asia, you will also find aluminium for applications where that pressure rating will allow that. And we can expect that this will also take place in Europe and US later on when it comes to problem solving related to weight issues, for example. Another important factor to stress is the explosive decompression. Hydrogen gas, due to its small molecular size, can permeate into the elastomer materials. Explosive decompression, also known as rapid gas decompression, is a failure mechanism that occurs in elastomer seals and O-rings when there is a rapid reduction in pressure of a gaseous medium. When a gas permeates into an elastomer seal and then rapidly expands upon pressure release, it can lead to fissures and seal failure. Absorbed hydrogen expands rapidly within the polymer, leading to internal blister fractures or macro cracks. But thanks to Parker's engineered materials group, we do have access to elastomer seals which allow us to protect our devices against that effect. If we think about the construction principles, we need to consider several aspects in our specification. In order to ensure the range of a truck or bus, the tank system are usually using mainly 350 bar pressure rating or nowadays also 700 bar. In order to meet the safety requirements for such pressure rates, appropriate safety margins must be planned. For us, for example, this means that we must be able to safely operate a solenoid valve that is specified with an operating pressure of 700 bar at a pressure difference of 875 bar at least, without problems or even causing damages. This is also the requirement that the licensing authorities have specified for the different standards, which I will go into later. But we also know the initial requirements of our customers who specify pressure rates. The background to such requirements lies in the properties of hydrogen and the worst case scenarios to be considered. For example, especially when refueling under extreme environmental conditions such as maximum temperature combined together with the Joule-Thomson effect, a maximum pressure rate of 960 bar can occur under certain circumstances for a valve that is normally designed for a normal pressure range of 700 bar. To speak about the Joule-Thomson effect, not all gases undergo a cooling effect upon expansion. Some gases, such as hydrogen and helium, will experience a warming effect upon expansion under conditions near room temperature and pressure, which might impact the behavior of our safety shut-off valves and pressure regulators. To consider the temperature range on board of a vehicle, I already mentioned the ambient and media temperatures, which can go down to -40 degrees C and more on the cold side, but also reach maximum temperatures of +100 degrees C, which has an important impact on our soft seals. Especially the minus temperatures do have a significant impact on the performance of our elastomer seals, but which has to be compensated with an appropriate strategy, which we do have. In contrast to stationary applications, the risk of flammability and ignition is significantly lower on board of vehicles thanks to adequate ventilation and does not require usually any further protective measures under normal circumstances. But the tightness is a very critical factor to stress as well. Besides the mentioned safety requirements, we should not forget that we are using hydrogen as a fuel, which has a cost and also ensures the range of our vehicle. So there are quite high standard requirements for leak tightness in place, not only caused by the standards and certification requirements, but also from the user side, who want to protect their systems against risks and losses at the same time. But now let's have a look at the last point of our list of challenges: approvals and certification. If we look at the framework conditions described with the risks shown, it quickly becomes clear that appropriate regulations are necessary for general use on our roads. Appropriate standards were introduced early on, and I would like now to give you an overview of the current situation. Already in the early 2000s, first standards were established. From the outset, it was the declared aim of all those involved to ensure maximum safety, not only to protect human health and investments, but also to achieve general acceptance of hydrogen as a fuel for the future. In the past, it was often the case that after the development of new technologies, first standardization took place before requirements for local or global approvals were defined. In the case of hydrogen application, it was different right from the start. The special conditions dictated by hydrogen and the associated risks immediately led to the development of international standards for a wide range of applications. Today, we find international standards for each and every application, even further developed to ISO standards. The latest evolution is now the ISO 19887, which is not yet released but in final preparation. But you can see here an overview about the current situation. In Europe, the EC 79 was applied for many years. EC 79 was a safety-related regulation on hydrogen-powered vehicles and hydrogen systems and components designed for those types of vehicles. Its scope addresses both liquid and compressed gaseous hydrogen. It was published in January 2009 and provided general requirements for type approval of hydrogen components and systems and to list applicable test procedures in the 27 EU states. For gaseous hydrogen tanks and components, it was possible to get type approvals according to EC 79 if their nominal working pressure is higher than 3 megapascal. Type approvals can be achieved for all kinds of components within the scope of the EC 79. Later on, the United Nations Global Technical Regulation came into place, which led to the HGV 3.1 regulation for the US and the ECE R134 for Europe, which do have many details in common, and the new upcoming ISO 19887 will cover both regions in one international standard. While the GTR 13 is developed under the UN 1998 agreement and is therefore not applicable as a guideline for type approval of vehicles in EU, The ECE R134 is developed under the UN 1958 agreement to provide that exact formal framework. The content and testing procedures described in both regulations are closely linked to each other. The UN GTR 13 contents are created by an informal working group and subsequently transferred into the ECE R134. Both standards providing rules for approving hydrogen vehicles and their components on a safety-related performance basis. Its scope is much narrower than of AC 79. As for both standards are only referring to the so-called compressed hydrogen storage system. As per definition, a typical compressed hydrogen storage system consists of the components tank storage container, container shutoff valve, check valve and TPRD. As seen here, many components are not shown in the are not covered, while the EC79 covered all of them. So showing now that the two regulations are not completely congruent. The ECE R134 does not include requirements regarding the electrical safety of the electric powertrain, post-crash fuel system integrity in the event of a collision, and material compatibility. Within the regulations is defined that the maximum service life of the hydrogen container shall not exceed 15 years, while it was 20 years with the EC79. All those standards are really requiring intensive testing and qualification. It has really a high impact and the cost for such certificates are quite incredible. So for a manufacturer it's quite important to have a solid specification in place which covers most of the requirements in the market to be able to generate a new product with a scope which covers a lot of different applications and functions to ensure that the investment in such a certification is properly covered and will provide a return on investment. So, but now we will move forward and I will hand over again to my colleague Steve, who will summarize and wrap up for the next minutes. Thank you very much. Steve, please.
Thanks, Christian. In wrapping up, I just wanted to mention that Parker is well positioned for the technology transition. We've been dealing with compressed natural gas and have all the fluid conveyance, control, and filtration products available on the industry, which has allowed us the ability to develop similar products for hydrogen vehicles. We have engineers that participate on several of these industry standardization committees and are helping assist in the writing of the standards, along with developing the products needed, along with the certifications and standards that those products need to meet to provide safety in the industry. Core competency in sealing and filtration of high and low pressure fluids and gases is something Parker has been dealing with for over 100 years. And through that, we've been able to develop a full breadth of product. In closing, I'd like to share a schematic of a hydrogen fuel cell electric vehicle. Whereas it looks a little complicated, this schematic is actually found at parker.com/hydrogen, along with product details on each of these items that represent fluid conveyance, fluid control, and filtration products. I'd like to thank everybody for their participation in the webinar today and let you know that there will be copies of this webinar available after the presentation. As you can see, our contact information is also attached if there are any additional questions that you would like to reach out to us. And at this point, I'd like to open it up to questions.
Thank you for that presentation, Christian, Steve, and Robert. A very comprehensive session, and I feel like those watching will really walk away with practical knowledge and insights into this emerging hydrogen economy. And as I mentioned at the top of the webinar, and as you've just heard from Steve, we do now have some time for audience questions, and there is still time to send yours in, so please do. Now, the first question that I saw come in was Danny asking, what do you use to absorb the dissolved gas contaminants? And I believe this was in relation to the stack. So who wants to take that?
Regarding the air filtration, as mentioned before, different types of gases need to be filtered out from the environmental air. There are several technologies which can be utilized for this adsorption. Currently, mostly utilized is activated carbon. And the activated carbon, depending on the impregnation which we have on it, it can absorb different gases and with different performances. There are a couple of additional technologies which work better with other gases like ammonia, for example. So there is a balance which needs to be done on making sure that the gases are absorbed correctly. However, we don't want to increase the pressure drop across the filter, and we don't want to make the filter too complicated. So we do have several filtration solutions and different filtration combinations where different technologies are used. And as mentioned, these are typically developed based on application requirements.
Thank you for that, Robert and Danny. I hope that's answered your question. Now, another audience question here from Roman, who asks, what are the benefits of hollow fiber in comparison to flat sheet membrane type humidifiers?
I think that's also a question for me. So as presented also on the last slide from Steve, we at Parker do produce humidifiers for fuel cell applications. We utilize the hollow fiber technology. The other technology which is in running, I want to say, is the flat sheet membrane humidifiers. So both of them are competitive. There are advantages and disadvantages for both. For example, the active surface area, which will impact the humidity transfer in the humidifier. With hollow fiber technology, you can have a higher active surface, which impacts positively the performance. Manufacturability of the fibers themselves is simpler on the flat sheet membranes. However, when we are talking about assembly of the humidifier, the flat sheet membranes are a bit more complicated because you need to make sure that you are sealing between each sheet, which gets quite complicated. Similarly, from durability point of view, potentially, the hollow fibers have a small advantage. Again, this is more due to the fact that you need to make sure that you are sealing between the fibers and between the sheets throughout the lifetime. And with vibration and other conditions, this can have an impact. Currently, there is no front runner, I want to say. Both of the technologies are still in development and in improvement phases. So, yeah.
Sure, thank you once again, Robert. Now, the next question I have is, which cleanliness class is required for the components, for example, fittings, hose assemblies, and so on?
I think I can take a stab at that. I'll give Robert a break here. You know, I don't think there's no one standard at this point. We've seen different standards based on the customer. The OEM might specify something in particular. I shared earlier in the presentation that there was a standard for the hydrogen gas at the refueling station. Obviously, the goal is to not allow any additional contaminants into the system to obviously extend the life of the fuel cell. So, you know, nothing, you know, we're not allowed to add any kind of oils, no type of grease, no dust. Basically, none of those contaminants would be allowed into the system. In fact, some of the hoses that we offer it's actually critical to understand the type of leaching that could occur. Again, making sure that there's nothing contaminating and adjusting or eliminating the life of your fuel cell. So.
Sure, thank you for that, Steve. Now we've had another question in from Daniel in regards to materials. And Daniel asks, which O-ring material is best for hydrogen use?
I'm not sure on the specific details on that. I do know that we've tested several types of O-rings and have a variety of material to offer the customer. So there is more than one. And obviously, if that particular individual wants to know a little bit more based on their specific application, we definitely be willing to help them out. Again, there's a lot of different variances in what we're seeing so far on board these hydrogen fuel delivery systems, right? Temperatures are a huge impact. Pressures, if you're at the high end versus the lower end, the pressure is a huge difference, and then temperatures fluctuate greatly as well, whether you're dealing with a high temperature constraint in the system or the low temperature could adjust the type of O-ring seal you're going to use.
Sure, thank you, Steve. And Daniel, hopefully that's answered your question somewhat. Now, an interesting question here from Joanne, who says, in your experiences, technology aside, how ready is the market for this technology? You might all have a take on this in your respective positions. Are we ready to accept over EV, for example?
Anybody want to take a stab? I think I'll answer here briefly. I think obviously EV from electric vehicles is ahead of the curve. I mean, thanks to Tesla and other car manufacturers, battery electric vehicles have been out there longer, and now those are being adapted into medium duty and in some cases heavy duty vehicles. So they've got definitely the lead. Now, where I think hydrogen will come to play is obviously there's some constraints in dealing in larger vehicles with the batteries that are required. And I think that's where hydrogen is going to have its opportunity.
Sure,
in some cases, a battery electric vehicle, if you think about it, here's another perspective, right? There's not much difference between a battery electric vehicle and a hydrogen fuel cell vehicle, except for the hydrogen. Basically, the same motors that are propelling the vehicle are on board. What you have the advantage of with the hydrogen is obviously now you're going to be able to extend the life of that battery while on the road. So if you've got a customer or an OEM that's already using a battery electric vehicle, it would be fairly easy or easier to convert to a hydrogen fuel electric vehicle.
Sure, thanks, Steve. And perhaps I'm wandering from the theme here a bit, but electric vehicles, as you say, you've got Tesla almost as their poster boy. Do hydrogen vehicles need something like this?
We do have several OEMs that are offering hydrogen vehicles today. The Toyota Mirai is an example of one. I guess that would be considered our poster.
Absolutely, yeah, I've seen them on the road. Now we've got a few more audience questions here, so we'll get through some of this. We spoke about hydrogen embrittlement earlier, so perhaps we could revisit that. How does hydrogen embrittlement affect the life of components?
That is a question I can maybe step in. The hydrogen embrittlement is a factor we have to consider from the beginning when we design the product. So we try to avoid to use any kind of materials which could have been impacted by the embrittlement itself. So in the early times when the experience was not there, sometimes the market used materials which are not suitable at the end of the day. Today, this effect has to be considered for the from the design engineers, but in reality, with the products we see today in the market, you will not face significant issues here. I spoke during the presentation about the incidents related with hydrogen. I mentioned 85% is related to human factor. Today, what we see in the statistics is that embrittlement is less than 3% affecting the lifetime, so and causing incidents. So it's important to stress it from the beginning, but at the end of the day, the product you will see and use in the field today should be good to go.
Thank you, Christian. We've got plenty more audience questions which have just come in, so we'll make sure to get through all of these. Vital asks, can you provide more technical information about the Joule-Thomson effect and how we can estimate how much heat it would generate in the system?
The question for physicists, I'm most probably not the right person to answer that. We consider the Joule-Thomson effect when it comes to temperatures and pressure rates. So we, as I mentioned, have, for example, requirements during the refueling period where due to the pressure and the temperature and the environmental conditions, the pressure might peak above the 875 bar for such a system. But the calculation modules, I think you can find the information really from the official statistics and the statistic formulas for that. I'm not here in the position today to answer that in detail.
Well, thank you for attempting that, Christian. Vital, perhaps you could hunt down a physicist, as Christian said. A couple more questions. Is a two-stage regulator setup required for stable hydrogen pressure for fuel cells?
So that depends also on the specification you have to fulfill. If the requested flow rate and pressure rate is not too high, then a single-stage regulator might do the job properly. As soon as it comes to high flow requirements, then a dual stage, second stage regulator will improve the quality of the regulation for sure. Yes.
Thank you, Christian. And one final audience question here is going to have a look towards the future. In regards to improving energy density, how high of H2 gas infrastructure pressure do you think that we're going to see in the next 10 years? Is 700 bar the standard?
I talked a little bit about that earlier. So yeah, I mean, the standard today is 350 bar and 700 bar systems. And in a lot of cases, the refueling stations can address both of those pressures. Obviously, the vehicle application will demand will determine what type of pressure is typically used. However, I do see in the future, 10 years out, 700 bar probably being the norm at that point. And then something else to look at is liquefied hydrogen. We're also hearing to get the range that some of the customers are requesting. Ultimately, we're going to have to also include liquid hydrogen stored on the vehicle as well.
Sure, thank you for that, Steve. And perhaps I should wrap up here now with one final look towards the future. One for all of you, perhaps, but what's next for Parker? Going forward, how do you continue to improve and what's next?
We're continuing to work with the OEMs out there in the industry today to help develop these systems, right? To provide the products that are needed for fluid conveyance, fluid control, filtration. We have engineers working on some of these committees that are developing the standards. Some of those standards have already been developed and are out there in the industry. Others we're wrapping up as we speak. So I feel we're able to take that inside information and generate the products that are needed for these hydrogen onboard fuel delivery systems.
Thank you for that, Steve. An exciting time ahead. And I'm just going to squeeze in one final audience question, which I've just seen sneak in here from Luke. Are you finding distribution stations utilising liquid storage and gaseous storage of hydrogen?
I think that's the preferred solution, right? I mean, At this point, depending on the volume that station is seeing, yeah, it's probably, good enough to deliver it in a gaseous form, and then obviously refuel your vehicle at either 350 or 700 bar. But I think the ideal application would be to store the gas as a liquid or store the hydrogen as a liquid on the site, and then use that to either refuel at 350 or 700 bar.
Thank you for that, Steve. And Luke, hopefully that answers your question, but just last week we held a storage and distribution webinar here on H2V Webinar, so perhaps you could take a look at that too. But sadly with that, we are out of time today. Our thanks once again to Christian Rohr, Steve Jarecki and Robert Josa, and of course the Parker team for their insights today. If you missed any of today's webinar, do be sure to go back and watch on demand. Subscribers to H2V can do just that at gasworld.tv, where you'll also be able to view our back catalogue of H2V webinars, including that storage and distribution one, all also available on demand. In the meantime, do be sure to visit h2-view.com to stay up to date with all the latest news in the hydrogen industry. Our final thanks of the day, as always, go to you, the viewer, in homes and offices around the world for watching and participating. But until next time, goodbye.